Ideal gas. In ideal gas, there are two formulae that you need to know for your calculations. The first one is your PV equal to nRT. So to bear in mind that P must be in Pascal, V is in meter cube, and normally in chemistry, they tend to use cm cube and dm cube. So to convert dm cube to meter cube, you have to divide by 1,000. Well, if you want it to convert to meter cube, you have to divide by 10 to the power 6 or 1 million. The second set of formula that is used is PV equal to mRT divided by mR. Basically, the number of moles is now being replaced by m, which is the mass, and mR, which is the molar mass. So because of this, you have to bear in mind that the unit for m is in grams. It's not the SI unit, because the unit of molar mass is in gram per mole. When applying this formula, there are two key assumptions made. The first one is that gas particles occupy no or negligible spaces relative to the volume of the container. And the second one is that there are no or negligible intermolecular forces existing between the gas molecules. However, it is imperative to know that the volume of a real gas is the volume of the ideal gas plus the volume occupied by the gas molecule. So in the case of ideal gas, we are assuming that this value is 0. In the case of the pressure of a real gas, is equal to the ideal gas, subtract by the pressure due to the attraction force between gaseous molecules. Imagine that if you have gas molecules that has springs connected amongst all of them, you will find that when the gas molecules collide on the wall, they will exert a lower force. And hence, the pressure of real gas is lower than that of ideal gas. Now let's take a look at the three possible graphs that could be plotted from looking at the ideal gas equation. Obviously, the first one is a linear one. And in this graph, we could actually have P plot against your temperature, all right, for Kelvin. This could be in Pascal. And certainly in this case, the value must start from 0, because on the Kelvin scale, temperature cannot be negative. So the graph would actually be a straight line. And the gradient of the graph would actually be NR over V. There's also another possibilities that we will plot P divided by 1 over V. In the case, if we have plot P divided by 1 over T, then we'll know that the gradient is in fact nRT, and this will be 1 over V. All right. So in this case, this will be your Y, and this will be your X. And in the same vein, the values will start from 0. The second graph that we look at is if you were to plot P against V. So in this graph, it will be the same as xy equal to k. And certainly, we can, as the temperature increases, or the number of moles increases, the graph will actually move outwards as sketched. The final graph that we look at is a horizontal line. This will be possibly when you plot PV over T against P or V. Because PV over T is actually equal to NR. It's actually equal to NR. So NR is actually in actual fact a constant value. And certainly if your N were to increase, then the graph will be moving upwards. Next, while we use PV equal to nRT, we tend to use them in SI unit. However, there are some questions that will require us to use non-SI units. So in those circumstances, we tend to use comparative analysis, which means that, like for example, in this example here, you find that the questions would have quite unknowns in the unit of atmospheric pressure, cm cube. And in this case, we can relative that to actually the RTP, all right, which is actually, you can sieve the data off from the data booklet, and you can retain the 1 ATM and the 24 dm cube where to convert to cm cube. We normalize the unit because we can then do a division. We can divide this equation with this, and then we can end up and manipulate the expressions and end up with this. So at times when we solve questions, there will be instances where you will use non-SI units and you have to do comparative analysis as exemplified here. Partial pressure. Partial pressure is defined as the pressure which the gas would have if it alone occupied the volume of the vessel at the same temperature. So it means that if we have a gas sample as such, and the total pressure is P total, this gas mixture comprises A and B, then the partial pressure of A will be if I were to remove the B molecules with only the A molecules inside in exactly the same vessel and at exactly the same temperature, then the pressure as a result of this is the partial pressure of A. Similarly, in the case of partial pressure of B, will be in the identical container and identical temperature, and we'll remove the molecule A with only the same number of molecules B that are present, and this will give rise to partial pressure of B. So based on this tree setup, we can now establish three equations. Let's now apply the ideal gas equation for each of the vessel. So in the case of PA will be this, in case of PB will be this one, and in case of P total will be this. And knowing that N total is equal to NA plus NB, we can then manipulate it till we end up with the expression that P total is the summation of all the partial pressure. But more importantly, this is the equation that we'll normally use for our calculations. All right, and your partial pressure could be calculated by using the mole fraction. In this case, the mole fraction of A, which is calculated by number of moles of A divided by the total number of moles of the gas molecule multiplied by P total. So these are the two equations that's typically used for calculation of partial pressure. Let's now take a look when two of the container, A and B, with varying volume is connected by a tap, and then what happens when the tap is open. Assumptions made is temperature does not change, gases do not chemically react, and the volume of the connecting pipes are negligible. So with that, let's apply the ideal gas equation for container X. So this will be the equation, well, this is the equation for container Y. And obviously we have an N total here, all right? So we could work through the mathematical expression here to finally arrive at this. This is otherwise a formula that is typically used for connecting two gases in different volumes together. And this will be the formula typically applied for such questions. Finally, for ideal gas, we have a couple of graphs to look at. The first graph is PV over RT against P, all right? So if it's an ideal gas, you find that this ought to be a horizontal line because the number of moles is fixed, while the rest of the other lines represent real gas behavior. In this graph, we are studying the effects of increasing temperature on the same type of gas. And you will find that as the temperature increases, the graph will tend towards ideal gas behavior. At high temperature, molecules have significantly higher kinetic energy. So with higher kinetic energy, potential energy is less significant, which means intermolecular attraction force between the molecules tends towards zero. That explains why real gas tends towards ideal gas behavior. Let's now take a look at low pressure. As pressure decreases, all the real gas also tends towards ideal gas behavior. The reason is because at low pressure, there's plenty of empty space, which means the volume occupied by the gas molecule relative to the volume of the vessel is negligible. And that explains why real gas tends towards ideal gas behavior. Finally, let's look at how various real gases deviates from ideal gas behavior. So in this graph, you will find that you may have gas A, B, C, D. They're all different gases. And we can conclude to say that gas D has the least deviation from ideal gas behavior, while gas A has the largest deviation from ideal gas behavior. And in the exam, they may actually ask you why that as pressure increases, the real gas deviates more significantly from ideal gas behavior. The reason is because at high pressure, particles are closer to each other. So the volume occupied by particles becomes significant, which means V real is larger than V ideal. So in this case, when you compute the value of PV nRT, it ought to be a significantly larger value, which is the reason why when pressure is high, all the PV-RT values of real gas tends to be higher than that of ideal gas. Let's take a look at the next question, which is why for real gas, the value of PV over RT is lower than that of ideal gas. And the reason is because intermolecular forces of real gas become significant. Imagine gas molecules that have springs connected amongst each of them. It means the force imparted by the molecules when colliding on the wall is now negated by the attraction force between each other. So thus the pressure exerted will be expected to be lower than ideal gas, which means P real is less than P ideal. So in this case, you'll know that PV over RT will be lower than the ideal gas value. Finally, if out of the 4 gases, A, B, C, D, if one of the gases is ammonia relative to the other 3, which is not able to have intermolecular hydrogen bonding, then we will expect gas A to be ammonia. The reason is because it has the strongest intermolecular attraction forces between the molecule, which is namely intermolecular hydrogen bonding relative to the rest of the other molecules.